All right, so starting our Chapter 1, Video 2 for Organic 1, CH4513. Um, Picking up in slide 11 of Chapter 1, Atomic Structure, specifically looking at electron configurations. For electron configurations, you should be familiar with a ground state electron configuration where you list out all of the orbitals that are occupied by electrons for any given atom. All right, and so there are about three rules we want to try and keep in mind here. First off is the off-ball principle, where you fill the lowest energy orbitals first as you put electrons into these orbitals. All right, and you can see this order of 1s, 2s, 2p, 3s, 3p, 4s, 3d. All right, and that is following the lower energy orbital. In this, out of all these listed, this one is the lowest energy, and this one here is the highest energy. Okay, and so big thing here is you notice 1s, 2s, then 2p, then 3s, 3p, but then right here this 4s to 3d, right, that might seem to trip you out and like, oh no, I got to memorize that kind of stuff. But just in case you weren't shown this in Gen Chem, you don't really have to do that, right? Specifically paying attention to the whole 3p, 4s, 3d, right? Let's actually go all the way to something that's in the 3D block. So if we were to pick chromium here that's in the 3D block, all right, as you recall, right, that's our first row, our second row, our third row, and our fourth row, right? So if you notice here, the S's start in the first row, so this would be 1s, and then as we come back around starting on the second row, we're now in the 2s. So it was 1s, and now here we're in the 2s. Then once we fill all the 2s's, we're now in the 2p block. All right, and then we come back around to the third row here, we're at the 3s. And you notice when we fill up the 3s, we go to 3p. All right, we wrap back around, we're here now at the fourth row. So this right here is our 4s's. I'm going to just put an arrow. I filled up the 4s, and you notice I've gotten now to the 3D block, right? So all of these right here are a part of my D block, but specifically 3D. Okay, so and then of course we hit up here. We're now coming back into the P block after we fill up the D. Well, I'm stopping at chromium, but if we had to go past that, say to bromine, you're going to see here we're going to fill up the 3D, then we're going to hit the 4P. So 4P1, 4P2, 4P3, 4P4, 4P5. So here we're in the 4P block, and if we were looking at bromine, its highest atomic orbital would be 4p, and it would go into the 4p5. That would be the last thing we would list in its electron configuration. Chromium here, we would see that we would get 4s and then 3d. And so when we look 4s, 3d, so 1, 2, 3, 4. I picked an awful example because this is that whole half-filled rule. You might think that it's 4s2, 3d4, but that is high. That's a high energy valence shell, and so it wouldn't actually do that. It would do this half-filled scenario where you would get 4s1, 3d5. So now both your s and your d orbitals are all half-filled. So this is more stable in terms of looking at our valence shell. Okay, and remember our valence shell is our highest number shell. Okay, so in this case, technically, for us, if we just said that we had one electron as a valence electron, that's fine. And then some people, they look at both the 4s and the 3d, so they could have said 6 valence electrons. All right. Okay, so anyway, that's the off-ball. Then looking at the Pauli exclusion principle, you want to match your electrons with spin. So for instance, if we have 1s2, right, that would be helium. Helium is 1s2. So when you talk about how electrons are in that 1s orbital, if I draw a box to represent it, I can't say that both of my electrons are spinning the same way. I can't do that. That is unforgivable, all right? So what you want to see is that they have to have opposite spin, okay? So electrons can spin either up or down, but when there's two electrons in there, they have to have opposite spin, opposite sign, all right? Next up, looking at Hund's rule. Electrons occupy orbitals with parallel spin until all orbitals have one electron. So that's more or less looking at a scenario. If we come back here to our periodic table, if we were to compare, say, if we were to look at nitrogen, for instance, if you look at it, nitrogen is 1s2. All right, we fill up the s's, then we get to the 2s, so it's 2s2 next. All right, and then here you hit the 2p's, so it's 2p3. 2p3. So when we look at nitrogen, specifically the p orbital, the p block part of our nitrogen, so these are my 2p orbitals. I have 3 of them. Right? So we notice that the p block was 2p3. So Pauli exclusion is, Hund is saying that we have to have parallel spins first. So it would have to be 1, 2, 3, or all of them down. 1, 2, 3. All right. I think most people prefer to be like positive and upbeat, so they always start with the up arrows first. I don't know. I'm just making something up here. But it doesn't matter. Both of these would be the correct way to represent those electrons in the orbital, right? These are correct, so to get your 2p3. Now, if you represented 2p3 like this, yet again, unforgivable. Right? We don't do that. That is bad juju, bad bantha fata, all right? As they say in Star Wars. All right. And so looking at kind of an example here, looking at sulfur. Sulfur on the periodic table, sulfur is 16, so we know that we're going to have 16 electrons to talk about. And also you can see we finish here in the 3p block. So when you see me write it out, we would write it out first: 1s2, 2s2, 2p6, 3p2, 3p4. And so filling in the orbitals, this is, I wrote boxes before. This is another way you could represent it, lowest to highest energy. And so you see you stop here at the 3p4, and so when you represent it, you're actually going to fill everything until you get to the 3p. So up, down, up, down, up, down, up, down, up, down, up, down. All right, and so you notice here, following our the first rule we followed, starting at 1s and then working our way up to 3p, was the Aufbau principle. And then the Pauli, in nowhere in here do we break the Pauli exclusion principle. You can see that every orbital has 2 electrons and they have opposite spin. All right, and then here, starting in the 3p, is where we can see our Hund's rule at play. So first, what they did with 4 electrons, they said 1, 2, 3. So they're all every orbital is half filled, parallel spin. And then they said, okay, the 4th one, now I can start putting in the opposite spin. All right, so that's how we would fill that in. All right, looking at chemical bonding. All right, carbon having 4 valence electrons, making 4 single bonds. We're going to see its most common molecular geometry with a tetrahedral, right? So having 4 domains, right? 1, 2, 3, 4 single bonds means that it has 4 domains around it. 4 single bonds, 4 domains. We're looking at a tetrahedral molecular structure. All right. And so some things to kind of pay attention to here. I'm saying that's the molecular structure. That's also tetrahedral in this case for CH4. That tetrahedral is both the molecular and the electron pair geometry. Okay, they both match. They're both tetrahedral in this case. Now, when does that change? Well, we want to look at something. What if we had, so that is CH4, right? What if we had CH3 plus with a plus charge? So what you're looking at here is you have carbon has 3 bonds with hydrogen and then a plus charge. So one of its orbitals are empty. So if you look here, you got 1, 2, 3. You have 3 electron domains. So you know you're not tetrahedral, you are trigonal planar when you talk about both the molecular and the electron geometries. All right, so in this case. However, what's another way? Let's look at a different scenario for carbon. What if we had carbon with a negative charge? Let's say we had CH3 and a minus charge on that carbon. So instead, you're looking at carbon has 3 hydrogens and then a lone pair on it to give us that minus charge on the carbon. Okay, I'll go ahead and represent up here. So now what you look at is you have 1, 2, 3, 4. You have 4 domains around it. So you know that its electron geometry is tetrahedral. However, when you talk about its molecular geometry, right? Molecular geometry, the lone pairs are invisible. So what you're seeing here is you have 1, 2, 3 bonds that you're going to pay attention to, and then this lone pair right here that I drew with the 2 dots is invisible. And so it's no longer tetrahedral. It's going to be trigonal pyramidal, all right? And if I misspell it, please forgive me, but I'm pretty sure I didn't. Trigonal, that's an O between the G and the N. Trigonal pyramidal, all right? So these two can differ, right? Which hopefully you remember, all right? And so anyway, when we talk about the chemical bonding theory, or chemical bonding in general, we are talking about valence electrons, all right? We're looking at when you did Lewis structures and stuff, you were looking at, let's find all of the valence electrons for each atom that's making up the molecule. All right, and so these valence electrons are what give us our reactivity. They give us our bonding. Okay, and so for carbon, we're primarily going to be seeing covalent bonds. Right, so over here in CH4, methane, right, CH4 there, those single bonds right there, those are covalent bonds, right? So those electrons are being equally shared between both the carbon and the hydrogen, equally shared between the carbon and the hydrogen, right? Okay, now you can have ionic bonds where, in essence, one of the atoms steals the electrons. Okay, so one of them is going to be electron rich, the other is going to be electron poor because its electrons were stolen, all right? Like a thief in the night. All right. And so, as I said earlier, right, you should be familiar with this chemical bonding theory, especially when we talk about Lewis structures. All right, you should have had some sort of introduction to the Lewis dot structure, because when you look at CH4, right, you know that based off of your periodic table, carbon has 1, 2, 3, 4 valence electrons. I only look at one row, the row that carbon is in. Okay, so 1, 2, 3, 4. So carbon has 4 valence electrons, and then each hydrogen right here has 1. So you're looking at 4 times 1. So you're seeing a total of 4 plus 4, or 8 valence electrons. And so you recall that you want to pick your central atom, and it's typically listed first here, so that's why carbon's in the middle. And then you put a hydrogen in each quadrant around carbon, and then you just put electrons around it. So you could have said C, something like that. I think we simplify it a little bit for you. I don't really like the dots. They're atrocious. They're overly complicated. That's too much to look at. So if you were to start with carbon in the middle and then put 4 hydrogens around it, you would put 1 bond between them. And as you recall, each bond is 2 electrons. So you have 2, 4, 6, 8 electrons in play. You had 8 valence electrons. So that is your Lewis structure. Okay, your line, or more specifically, we call this the line bond or Kekulé structure. Right, where we only show lone pair electrons when they're not bonding. So here on ammonia, right, nitrogen has 1, 2, 3, 4, 5, right? So nitrogen has 5 valence electrons, and then each hydrogen, as we saw earlier up here, has 1 valence electron. So you're looking at 5, 6, 7, 8. So yet again, you're looking at 8 valence electrons. And so when you start out with nitrogen in the middle, you know you're going to have 3 hydrogens around it because it is NH3, right? You're going to start with 3 hydrogens around it. And if you look, you need to account for 8 valence electrons. So 2, 4, 6. Right there, that is 6 valence electrons. and you know you need a lone pair to give you that 8. Okay, and you could repeat this with water or methanol. All right. All right. And so at this point, I'm going to stop here, and we'll pick up with a third video.